Okay, this is the eighth lecture by Harvey Friedman on invariant maximality reversal, part 6. Please.
Yes, thank you. Today is section 4.5. We skipped 4.6 because that's a pure, boring bookkeeping section, um, which I can talk about more when we get into, not now, but what am I bookkeeping? We can get more into that, not in this lecture so much, but subsequent lectures. What am I bookkeeping? But uh, that's not kind of too relevant today. And section 4.7, the lecture is now on Andreas's site, and the uh, and in uh, the version, the official version of the in full, which has all the proofs and everything, that's already done a couple of days ago or so in my downloadable manuscripts page. And that's the pattern we're going to follow for this section 4.5. So I always refresh where we are, uh, the overall view here. And we are reversing this statement. Uh, every ordered invariant graph on Q minus 1, 1K has a invariant maximal clique. And if you remember, without this, invariant just means you're mapping 0K to 1K and 1K to 2K, dot, dot, dot to K, all the way, it's just a shift thing. And that's provable, although it does take some ideas because of the endpoint. It's not just a pure Ramsey theoretic thing. It's, but when you put this on here, it needs large cardinals, the SRP hierarchy, because these are the parameters. So that's the usual review I give every time. And this is implicitly pi 0, 1, using Gödel's completeness theorem. And I've said this many times. And uh, yeah, so and there's some very nice explicitly pi 0, 1 forms of this we'll eventually talk about when we finish the reversal, uh, that have been quite successful, I think. All right. So we're in this reversal, which is chapter 4 of the book. And this is the familiar 11 sections, of which we did 11, 10, 9, 8, 7. And now we're doing 5. Okay. Um, so I decided that I should now talk a bit about how this reversal works in some detail, some aspects of it at least, from all the way from 4.3, but we're going to focus on 4.5. But the trouble is that if I don't give this content, this may not make as much sense as it should. So we're going to add some context um, to what goes on here leading up to tupling. So 4.1 and 4.2 are preliminary sections. Notation, terminology, how do I talk about a graph without actually writing it all down because it's too long? Maybe the full graph appears in here. So really the reversal starts in 4.3, where we actually start assuming the statement being reversed. That's when we start assuming the statement reversed, right in here in 4.3. And we start with a where the complexity is not thrown at you all at once. A complicated order invariant graph on Q minus 1, 1 to the K, this should be to the K12 power. Recall that K12 is 12 twos with a K on top. So K of 1 is just 2 to the K. K12 is K2s, 12 twos with a K on top. Taking on we take an arbitrary maximal clique according to the statement being reversed. We take an arbitrary maximal clique in the graph, which is in fact invariant. Okay, that's how we start the reversal. And we make heavy use in 4.3 and 4.4. Not as much in 4.5 today, but in sections 4, 3, 4, 4, we make heavy use of the invariance, this invariance of the arbitrarily picked maximal clique to be invariant, applied in several ways to the system Q minus 1, 1 less than S. That's a convenient way to encapsulate this structure, Q minus 1, 1 and less than S, with these acting as indiscernibles. In fact, what I do, oh, I already see that I did this wrong here. Yeah, 0 over K, sorry. Yeah, I probably should, yeah, let's make this a little cleaner. Yeah, it's that structure. Um, yeah, with these acting as indiscernibles. Let me just put it in here. Yeah. But these are, these very special indiscernibles associated with this, right? Parameters here and shifting over here. No moving around stuff as in normal indiscernibles, just actually the shift. This is very mathematical, this is very good for the propaganda. Okay, we develop both atomic representations for sets suitably defined and indiscernibility, okay? These representations and indiscernibility use certain finite languages. Now, let me stop here for a second. Atomic representability. Okay, now everybody's familiar with omenality and the stuff you get with real closed fields and other things, where everything definable, even including everything definable, including with parameters, is equivalent to a quantifier free formula. You don't get equivalent to atomic formula. You don't get connective. You don't get connective elimination. You only get quantifier elimination and omenality. Quantifier elimination, not connective elimination. Whereas here, whereas in set theory, I keep saying this, in set theory, you actually get um, uh, quantifier and connective elimination because it becomes equivalent to a epsilon x, where the parameter is x. You see, maybe I'm not using good letters here. The parameter is x, the set, and the statement is equivalent to a epsilon x if the statement is about a given domain. Okay, but you understand what I'm trying to say. So, and in this subject here, it's very important that you also have atomic representations. It won't be something as simple as epsilon. It'll be atomic representation. We're not doing set theory directly, although we did finally in section 11. So. Uh, it'll be an atomic representation, and we have a very primitive language here. Actually, the representation won't even use less than; it'll just use s, and it won't. And And what will happen is that we will use a lot of parameters. We will be using a lot of parameters, not just one as in set theory. Uh, and uh, the parameters are going to be these indiscernibles will be used as the parameters, but a lot of them. Now, the whole point of section 4.5 that we're doing today is to get it down to five parameters. Five parameters. Now, I could have gotten away with something more than five, but it naturally goes down to five. And what you need is the number of parameters being independent of a lot of other things, right? You need a number like five is good. All right. So these representations in indiscernibility use certain finite languages. Okay, so in this reversal, uh, we're going back to the early parts of the reversal. We only get indiscernibility and atomic representation for sets defined in certain finite languages. Now, if you remember what happened is because we went backwards, if you remember, um, is that this language slowly but surely for the representations became full, unrestricted quantification, well, always limited in some way, limited less than some place, but it became arbitrary. We're doing a real ordinary languages, L of K actually, I called it which is a language which has arbitrary number, infinitely many variables, and arbitrary finite complexity. And then finally, even later, it took a while later, so that the indiscernibility was also for the full language. You see, not just this finite language. So you can think of this reversal as having one thing about this reversal is that the languages start off finite and they're improved and improved to be normal languages at some point, where the reversal goes into sort of normal channels. So there are three languages that actually come up in this reversal. This is by far the most important language, but these other two are needed in sections 4. These sections, the other two languages appear in sections 4.3 and 4.4. These two languages don't appear in 4.5 today. These are totally irrelevant. They're auxiliary languages to help work with this language. These are auxiliary languages only, technical auxiliary languages. Um, Now, when I say it's applied to this structure, that's a little bit of a misnomer because a little bit of a lie because this K indicates they're only using a K area relation. This K over K4 indicates we're only using a K4 area relation. This is, of course, 4 2s with a K on top. And this one uses a relation of size of arity K8. But we actually take S, and as we for this language, we look at S/K, a way of forcing S to be a K area relation. I define that explicitly below, and then for this language we make S a K4 area relation, and for this language we make S a K8 area relation. All right. So the first of these languages use quantification. Definitely use quantification. Used throughout 4.3, 4.4, and 4.7, the thing that we did last time, the big development. The last two of these languages are quantifier free. That's what the zero means. They're quantifier free, and we use them only in section 4.3 and 4.4 as auxiliary technicalities. All right. Now the end of section 4.3. And remember, 4.3 is the first serious section of the reversal, where we assume the statement being reversed. In section 4, the end of section 4.3 features both of these things with atomic representation. Atomic representation. These two languages are already quantifier free, so quantifier free elimination would be meaningless. Atomic representation. Okay, so in section 4.4, we move from this. Actually, maybe I should now put this right in there. Um, uh, we move from this structure to some structure like this, where the indiscernibles are no longer, yeah, I should fix this. Oh, I think there's something I'm saying here that's wrong. Yeah, sorry. I'm oversimplifying something here in uh, this thing here. Yeah, I got to make sure I never do this again. This is much more fine-tuned, these indiscernibles. Yeah. Yeah, we have a lot of indiscernibles from the statement. The number of indiscernibles in the statement being reversed is the same as the dimension. It's convenient to have them both the same. And uh, that's proved in section 2. That's proved that having them the same does not weaken the statement. The full statement, when the dimension and the number of indiscernibles is the same, is equivalent to the statement when you have the full statement when you have any dimension and any fine-tuned indiscernibles is the same. That's proved. Okay. Okay. The end of section 4.3 features, yeah, we already discussed this. Okay. And uh yeah, the three different ways of doing that. All right. So okay, there's a big deal that we do here in section 4.4. We actually, it's called negative reduction, section 4.4. So we actually move to the negative numbers only, and we have infinitely many indiscernibles. You see, the statement starts with only finitely many. We're not going to stretch these because we already got to the top. These indiscernibles are go all the way to 1, so we're not going to be stretching them. But we're going to do something. We're going to do some magic where we simultaneously throw everything in the negative world, and stretch them to an infinite sequence of indiscernibles, where the soup of the R's is 0. This is what 4.4 does. And the title of the section is appropriately called negative reduction. See, this step in section 4.4 is important. with the soup of the R's is 0. We wind up with a stronger indiscernibility, actually. You even get more. Section 4.4 is kind of magical. We wind up with a stronger indiscernibility than the latter when we have uh, than the latter in the latter than we have in here. And we wind up with an atomic representation and these indiscernibles both for this structure here. Yeah. So section 4.4, we wind up only talking about this most important finite language with indiscernibles and atomic representation. See, now that pattern um, persists, as you know, going forward, because we went backward and we kept seeing representations and indiscernibles of various kinds, more and more strong. Uh, okay, so now in this section 4.5, we work entirely at the end of uh, aside from some slight light auxiliary use. Yeah, so there's the transition isn't totally pure, although I probably could rewrite things to be that way. I don't think it's worth it. There's some backpedaling. There's some backpedaling to here, some minor backpedaling uh, to here, but it's a little technical. Okay. Yeah, and section 4.5 ends with an improved atomic representation only for this language, for this structure, but with the same indiscernibles for this that we had for before, the same indiscernibles, uh, they're really analogous because they're really not on the same quite structure. Unimproved. Okay, then we lift from here to here. So at the end of 4.5, we lift from here to here with an order-preserving map, or R is a K-O relation, removing arguments from S. Uh, that's probably not a good thing to say. This is already removed. Okay. I mean, the end of section 4.5, we've already discussed when we started 4.7. Okay, that's not new. All right. Now, it turns out that this improvement in the atomic representation um, for this over what we had over previous is just a matter of reducing the number of parameters used from over previous in the manuscript because we have been going backwards. It's just a matter of reducing the number of parameters used from gigantic to 5. So that's the whole point of this section 4.5, is the reduction of the number of parameters in atomic representation from gigantic to 5. Okay, so here's some more details. By the way, for those of you dying to see what I mean by cutting the arity down, this is the definition, crucial definition. You remember the star K12? What this means is you stretch X by repeating the last term so that the whole thing becomes length K over K12. This means you take X, which is short, and you um, stretch X to be of length K12, which is the biggest number around in this whole book, in this whole reversal, by repeating the last term of X so that it stretches out. Okay, so back to this. So that we have these three languages, and the first language uses atomic relation symbol RK, the second one atomic relation symbol RK4, and the third one RK8, which are of course of these arities. So the last coordinate in these finite languages is the arity. The other ones are respective. The other ones are the number of. This one is the number of variables. The number of variables starting from V's, I think V0 or V1, I can't remember. Doesn't make any difference. And this is the complexity, the logical complexity, the standard logical complexity notion. Okay. And this one has quantifiers. This is the most important one and has quantifiers. These are technical auxiliary ones that are quantifier free. So we still want some connective elimination, some connective elimination for these. We already have the quantifier elimination because there never were any quantifiers. Okay. So now we're ready to get going. Here is what section 4.4 ends with. So we can start 4.5. Remember, by popular demand, we're doing this reversal backwards. We're talking about it backwards. Okay, so it ends with two theorems, 4.4.16 and 4.4.17. Okay. 4.4.16 is the um, atomic representation that we get with massive numbers of parameters. Okay, if I have a formula now, phi A means this is according to an enumeration of the formulas, which is explicitly given in early section in even before the manuscripts, the reversal already starts. There's an enumeration of all the finitely many formulas in here, which has to respect complexity. So every formula appears in the enumeration after all the things of lower complexity appear. Yeah, you have to do that. Okay, so um, and then I have this is and then I have an assignment. I have an assignment uh, which is a K1 tuple. Remember, they're only K1 variables, so the assignments are of length K1. The assignments are always the same length as the number of variables. Okay, and they only go up to Rn. Remember, the R's are these negative indiscernibles. The R's are these negative indiscernibles that are increased strictly, and there are infinitely many of them. Okay, so that the formula being the formula for the quantifier elimination holds if and only if this atomic formula holds. Okay. Remember, S itself is K12 array. The quantifier elimination only involves these first K things, but S itself is very long. S over K is only length, it's K area. S itself is K12 area. Okay, so you see that's a natural, very nice atomic. The number of indiscernibles is 2A plus 1, where A is the position of the formula in the enumeration. So it's really quite uncontrolled. It's only barely controlled, the indiscernibility. Um, and in section 4.4, we work hard to get this with the R's. And then that's the uh, representation side, you know, which ultimately morphs into way, way, way later in the reversal, like section 7, but morphs into separation, separation. All right. And then the indiscernibility. Now, this looks complicated because I wrote it out in such gory detail. It's only for formulas. Uh, it's only for formulas in this finite language. And it basically says, you can just look down here, basically says that the R's can be moved so that they're order theoretically moved, order preserving moved. The parameters X are below everybody in here, right here, you see. And the quantifiers are all limited to either Rn or Rm. In other words, part of the indiscernibility is I don't care how far, I don't care where the quantifiers range over, as long as they're ranging over in the places below an indiscernible. So that's the kind, this kind of thing stays a long time, as you know, not really improved on in the thing. Right now, we're talking about this kind of thing, which gets improved, you see, we're now in section 4.5, but it gets improved in 4.7, as we saw last time, very strongly improved. All right. So this section is called tupling. It's called tupling because the whole point is to radically reduce the number of parameters used, radically use the number of parameters used in 4.4.16. In other words, we want only 5 things here. We don't want 2A plus 1 things. And by the way, A can be very large. The number of formulas in here is quite large. It's several exponents on K. I mean, it's not 12 of them, but it's many exponents of K. I can't remember. K, 2 to the 2 to the 2 to the K, or 3 of them or something. I don't remember. That stuff is done in the section, preliminary section 1, the estimates on how many formulas. All right, so tupling. So there's a preliminary lemma that looks mysterious that does involve going back to the system with, you see it here, that goes back, it does go back, it's a preliminary thing. It does go back to the system with positive numbers. It does go to some positive numbers, even though we're really care about only negative numbers now. We have to use this. So, so if we have a tuple of negative things, uh, S fails of 1 and X. This is going to be a K12 tuple, right? Yeah. This is technical stuff that is remnants of stuff in earlier sections. And there's a unique P. So this is a tupling lemma. There's a unique P greater than max X, such as S of PX, and this P is less than 1. Well, that's clear from here. Um, and then we have a uniqueness theorem, S of PX and S of PY, where P is bigger than the max of both of these things being equal, then X equals Y. As you saw in the last lecture, this idea of things being 1, 1 only when things have the same max, is a theme throughout this until way late in the reversal, All right. Assume furthermore that that we already get equality between them a little earlier, at some early point here. Then the unique P greater than max X is negative. All right. So in other words, we stay in the negative thing. This is a technical thing, and it's not. It goes deeper into 4.4 than just the end stage. So we have to do this. But the whole point of it is this, and this is just negative. This is all negative. So if we have a negative x uh, of length, a pretty heavy length, I don't want the length to be all the way up K12, but I want it to be like K5. Um, then I get a unique P greater than max X. And this unique P is less than the indiscernible Rn. So Rn, this is kind of a closed system, -1 Rn, right parenthesis. And the exponent, yeah, it didn't have to be that, but it can't be really big, even much bigger it can't be. All right. So this gives us a tupling facility, which we use in order to do our main work, the refinement of 4,4,16 from a large number of parameters to only 5. Okay, now. Okay, now this one is our starting point for getting serious. Um, okay, we already are assuming from 4,4,16 that this thing is equivalent to an atomic formula. All this says is, all this is doing is asking, um, all this is doing is restating this because I'm going to code. These are the parameters that are used in that 4,4,16. These are the parameters that are used. And all I want to say is all I want to say is if P is the code for them, in this kind of coding that we just talked about, or tupling, then I can restate this by asking what is P coding and say that that does it. So this thing is equivalent to saying there is a Y, which is going to have to be the R the actual parameters for the quantifier elimination. And I ask there is a Y such that Y is coded by P and Y does the work. And I only really care, I'm actually weakening things a little bit. I only really care that the max is the last term that I'm interested in, that last term that's used. So this follows from pure logic, plus the fact that we're doing this coding mechanism with, that we talked about. Okay. So this is all the negative region, which we want to stay. That was an aberration that I have to start off doing something with a number 1, you know, for technical reasons. All right. Okay, this is basically existentially quantifying out the numerous but fewer than k over 4 parameters in the atomic representation. Uh, uh, yeah, I think one computes that there's at most k over 4 parameters because the number a is quite a bit smaller than k over 4. I mean, the number of formulas is, yeah. All right, so now we look at the k over k4 dimensional y that have this property in 453, and we rewrite that property for y as follows. Uh, so this is the property. I just copied this. This is copied from the previous thing. The property uh, of y. Yeah, this is the property, and I want to rewrite this and put this in a form that's atomic. You see, I can do this. Uh, yeah, I put this in an atomic form, in this atomic form. This requires some guts from the previous sections. This is not just a superficial thing from what I say in 4.4. Uh, this uses so notice I put this in a form that uses this highest of the indiscernibles that I want to use for my 5, for my the original indiscernibles use as parameters, but with 2 extra numbers that come up. The last two in my given indiscernibles from the beginning, remember, they go up to one. Okay. This is written in atomic form with one negative indiscernible and two positive indiscernibles. The negative and positive indiscernibles mix well. That just means that when I actually did 4.4, I actually had some interaction. See, in order to get these negative indiscernibles, I had to use the positive indiscernibles and make them negative uh, with witnesses because of the fact that the negative ones are used as parameters in the indiscernibility statements. This is a little bit vague, but when we go through 4.4, we'll have to see this. There's these mix. Then the existence of K4 dimensional Y with the critical property as the form of the existentially quantified atomic formula here. Uh, 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 as which the existentially quantified one was earlier, sorry, which because of the presence of these three things, yeah, so we existentially quantified over this in the previous statement. So we're existentially quantifying now over this because it's equivalent. Now, existentially quantified atomic formulas are very well controlled. Existentially quantified atomic formulas become negated atomic formulas just from the maximality of S. This is something that's used all through sections 4.3 and 4. So we actually get this. This is copied again. This is copied again. This time it's equivalent to a negated atomic formula, but only with these five indiscernibles. It's really four indiscernibles that's added to one of the parameters, this parameter. It's four additional ones. No, three additional ones. 1, 2, 3, 4. Yeah, maybe did I leave one out here? 1, 2, 3, 4. Wait just a second here. Yeah, I must have left. This must be wrong. I think that this must be, yeah. My gosh, I don't even know how to count. You see, I reduce, okay, I reduce this quantifier, I reduce this existentially quantified statement to an existentially quantified statement, existentially quantified uh, negated atomic statement. See, this is what's happening. Existentially quantified, I reduced it to a negated, this existentially quantified statement gets reduced to a negated atomic statement. And that comes from just superficial stuff connected with the maximality. Okay, so I know this is a little bit one, two. I wonder why I did this. Maybe there's something that has to be fixed. I don't think so, but 2a plus 2. Maybe I don't know how to count up to 5. There we are. Yeah, I'm sure that that's all there is to that. Okay. Okay, now this here is not quite what I wrote here, but all you do is you apply this here to the given formula. You apply the given formula here. You apply it to not phi. This languages are closed under negation. You apply it to not phi, and then this becomes not, which is this. Okay. Believe me, I don't want to do intuitionism in this subject. All right. So we've gotten rid of the negation. Okay. So now we combine that with 4.757, and we get, well, I'm just reviewing 447. I just copied it. It's not changed. Then we get uh, this structure, um, which has properties of a model theoretic nature that's usual. Here's some more details. What we get is this from what we did. We get this lemma. We get a structure T. Yeah, sometimes I'm writing the relation before the indiscernibles, and sometimes I'm writing the indiscernibles before the relation. I promise to fix that so it's uniform throughout the book. Okay. All right. Has the following property. So R is a k-area relation, less than is usual ordering. The indiscernibles are, as I said, they're all negative. How about this here? They're all negative, converging to zero. Um, we have this tupling that I use to do everything else in this section, but we just stated on its own that there's a unique P bigger than max X such that RPX. You notice that this gets carried quite a bit in forward, excuse me, in the reversal, this kind of tupling. Um, and if X and Y have the same max and the same unique P, then they're equal. If max X is less than Rn, then the unique P is less than Rn. So the Rn's form a closed, the numbers below are the nth indiscernible form a closed system, pretty closed system, for regard to tupling at least. Then we have the atomic representation. Um, so given a formative phi and an indiscernible number, Rn, we can find five parameters somewhat higher than Rn. That's what we were always expecting, somewhat higher up, such that for every x, sat is equivalent to R of x with the five parameters. That's what we got from all that stuff we did. And then the indiscernibility has not really changed much. It's just this thing that you can move them around. You can move the indiscernibles around, keep with parameters below the first indiscernible, as long as you keep the same order. Yeah, and less than this. Yeah. All right. Now, the end of section 4.5, which is where we want to be today, finishes with a move from the negative numbers to this. And this is very convenient because instead of staring at R of one, R of two, R of three, we're going to stare at one, two, three, four, five. All right. I mean, it's just a convenient shifting. Uh, there's nothing deep here. There is one point though, which we'll see, which in order to do this right. So when we do this, we get this. We actually get this is the end point of section 4.5. We get a structure 1, 2, dot, 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 with the following properties. Less than is usual ordering on Q 0 infinity. R is a k-area relation on 0 infinity. We call it R now, not S, because we're moving the domain, uh, to non-negative numbers from negative numbers before. This is the tupling, not changed from what we said. And this is the critical representation with the five parameters. Uh, yeah. So Right. We don't have that these parameters are actually indiscernibles. We don't have that. Uh, we had that. That's a good point. In the atomic representation, we do have the parameters are indiscernibles early in the manuscript, but not not here. The reason I think you can do that, but the number wouldn't be n plus one, of course. You can't have numbers between n and n plus one that are integers. I think that we don't do say it that way, even though we could, because we want this to be smaller than the next indiscernible. That's right. We want this to be smaller than the next indiscernible. So I'll make that clearer in the final form of 4.5 that, you could make them integers and make this bigger, but we prefer to do this way. Uh, okay, so, and then the indiscernibility is the same. Now, in order to do this, we have to, it's not just a straightforward, it's almost a straightforward translation from order. It's almost a straightforward translation, mapping from uh, mapping between order preserving mapping between -1, 0 and 0 infinity. But because of this in the atomic representation, we need to work with we need to look at an arithmetic progression, so to speak, of the R's. You see, because we have five different R's that are coming up. You see, so we want room. See, there are five different things in here. Yeah, we want we're jumping up by this much. So we want to use these. So that doesn't affect the indiscernibility. In other words, we only want to use some of the indiscernibles, skipping by an arithmetic progression type in this statement, and then um, we make the isomorphism. We can use any isomorphism between this onto this. See, we want to skip over these things, and we define the k-area relation R on Q0 infinity for M as the inverse image of the k-area relation under the isomorphism. So it's almost straightforwardly just shifting from -1, 0 to 0 infinity, except we just have to cut the indiscernibles back some in order to make sure that these numbers 1, 2, 3, so that these numbers become indiscernibles. Uh, Here, these numbers, the 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 non-negative, the positive numbers are indiscernibles here. I'm sorry, not I'm in the wrong place. Positive numbers are indiscernibles here. See, okay, all right. I try to make this as simple as understandable as I can, but it's a little bit technical. But now I think, and I'll do a super polished checking on it in a few days. All right, so I think that I'm finished for today. Andres?